Alright, hello everyone. In today's video, we are going to be taking a look at a tank comprising 30% benzene and 70% toluene. And basically what's going to be happening is we are going to have this piston up here that is either going to be supplying pressure to the system or reducing the pressure in the system. And we're going to look at the bubble pressure, bubble temp, dew pressure, and dew temp. And basically what the bubble pressure here is it is when you have liquids in the system, and it is the pressure that the first bubble forms within the system at a constant temperature, and then the bubble temperature is just the reverse of that. It's when it's the temperature the first bubble forms at a constant pressure. And then over here for the dew pressure, that is just the point where the first liquid molecule forms within a mixture of gases at a constant temperature, and then the dew temperature is the temperature that the first liquid forms at a constant pressure. All right, and we're going to be using two equations to help us figure out what these pressures and temperatures are going to be. And that is going to be Raoult's law and the Anton equation. And we've already gone over the Anton equation in previous videos. So if you're not exactly sure what that is, you can go ahead and check out those videos. Alright, so Raoult's law up here is basically just saying that the mole fraction in the liquid phase times the pure saturation vapor pressure is going to be equal to the mole fraction in the gas phase times the total pressure. And basically this right side here is pretty much just the partial pressure of each compound. And now we're going to go ahead and we're going to figure out what our equations for these pressures and temperatures are going to be. So basically, we're going to solve for pressure right here. And we know that pressure is going to be equal to the sum of the partial pressures, all right? And since we know that our yi times p up here is the partial pressure, we know that the pressure is just going to be the sum of this left side up here, all right? Because that's the sum of the partial pressures right here, and we know that's equal to that. And we also know the temperature. It's going to be a constant temperature that's going to be given to us. So we are going to find this saturation pressure up here. So P is going to be equal to the sum of Xi times Pi sat. And that is going to be our equation for the bubble pressure. Now for the bubble temperature, we are going to need to doing some substitutions because we are now going to be given the pressure and we are not going to know what the temperature is. So basically what we're going to do is, since we know P sat down here, we're going to go ahead and do some logs and get this isolated by itself and then substitute that in, since we're going to have the temperature, and that's what we're going to need to solving for. We're going to need to solve the temperature, and that's why we need to get it into the equation. So we're going to go ahead and substitute that in. Alright, and there we go. That is going to be our equation for the bubble temperature. Now we're going to go ahead and move on to the dew pressure. In order to find the dew pressure, we are going to have to think about things going on in here a little bit more. So we know that we have 30% benzene and 70% toluene in there. And basically what we need to know is that the mole fractions of the liquid phase is going to add up to 1, right? You're never going to have more than 1, you're never going to have less than 1, alright? The mole fraction are always going to be equal to 1. So we can go ahead and set the sum of Xi equal to 1, because that is the sum of the liquid molar fractions. So that's going to be sum of Xi is going to be equal to 1. And we can go ahead and divide that Pi sat over, and we're going to get the sum of Yi times P over the saturation vapor pressure. Alright. And what we're trying to solve for here is this pressure right here, this P. So we can go ahead and take that out of the sum. And here we go. Now all that's left to do is we can just divide all of this by 1, or excuse me, divide 1 by all of that, I should say. And that is going to give us our equation to solve for the pressure, which is what we want. So I'll just go ahead and erase this here. So P is going to be equal to 1 over the sum of yi over pi set. And there we have it. That is going to be our equation for the dew pressure. Now for the dew temperature, we're just basically going to do the same thing we did over here for the bubble temperature. We're going to use the Anton equation to sub in for the saturation vapor pressure so that we can get T within the equation so we can solve for it. So P is going to be equal to 1 over the sum of yi over this Anton equation over here. Alright, there we go, and there we go. That is going to be our equation for the dew temperature. And yeah, we have all of our equations laid out now, and now we're going to go ahead and hop into Python and create a simulation for this. Alright, so now we have hopped into Python, and we're going to go ahead and write out some functions that are going to represent our bubble pressure, our bubble temperature, and then our dew pressure and our dew temperature. And I've already gone ahead and imported all the systems we're going to be using to write out this code over here. And so now we're going to go ahead and hop into the functions, alright? And the first thing we're going to want to do is we're going to write out some arrays that are going to represent the mole fractions in the liquid phase and the gas phase. So we're going to go ahead and go x is equal to np.array, and that's going to be 0.3 and 0.7, representing the percentage of benzene and toluene in there. And we're going to go ahead and do another one for y to represent the gas phase. So we're going to paste that on down there and write that in as y. Alright, and now we're going to go ahead and jump into our bubble pressure because that's probably going to be the easiest one for us to do. That one's pretty simple. So we're going to go define BP, and we're going to have to input x and t for that. Alright, and then we're just going to return the function that we derived in the first part of the video for the bubble pressure. That's pretty simple. That's just the sum of the mole fractions in the liquid phase times the pressure, which we are going to have since this is going to be at a constant temperature, right? Because we're trying to solve for the pressure, so we're going to be given the temperature. So it's going to be np.sum, and that's going to be x times p.pvap of the temperature that's going to be inputted. And there we go. That is going to be our function for the bubble pressure right there. And now we'll go ahead and define our function for the bubble temperature, BT. And that is going to be inputted with x and p this time, like so. Alright, so our function for the bubble temperature, we are going to have to realize that the temperature is going to be when the bubble pressure over here that we calculate is going to be equal to the constant pressure P that we have right here as a given. So basically what we're going to be doing for this is we're going to have a root function, and it is going to solve for when the bubble pressure is going to be equal to this P over here. And we're going to do some basic algebra, and we're going to set this BP minus P is equal to 0, alright? So we're going to go ahead and write out that function. And to do that, we're going to write out an equation over here, and we'll just give it a vector for now. And there we go. And we're going to set out an array over here so that it can perform the proper calculations. And we'll give it 0. And then that's just going to return over here our bubble pressure function minus the pressure, right? And the root solver is going to go through and test out a bunch of different temperatures until those two equations are equal to each other and equal to 0. And then that is going to be our bubble temperature, all right? So this is going to return BP with X and T. And then that is going to be minus P, all right? And then we are going to go ahead and return the root solver. And then that is going to go through and solve this EQ over here. And then we're going to have to input a guess, so we'll just do 298 for room temperature. Alright, there we go. And then we'll do .x and then 0, so that we can pull it out of array form and get a simple answer out of it. Alright, and we'll shift enter and make sure that's all running right. Alright, looks like it's working well. Alright, so now we're going to go ahead and follow pretty much the same exact logic that we used to get our bubble pressure and bubble temperature functions to figure out our dew pressure and our dew temperature functions. So we're going to go ahead and define our dew pressure function, and this is going to be using the mole fractions in the gas phase this time. So we're going to be using y instead of x, and this is going to be equal to the MP dot sum of 1 over y over the P dot PVAP at the given temperature that we're going to input over here, like so. Alright, and that should be working well, and there we go. That is going to be our function for the dew pressure. It's simple enough. And now for the dew temperature, we're going to have to do the same thing we did over here for our bubble temperature, and we're going to have to use a root function because, once again, we're going to need to set it equal to 0, right? So we're going to have, we'll just go ahead and write it out. We're going to have dt, and that's going to be y, and we're going to input the pressure this time. Pressure is going to be a constant. Alright, and that is we're going to go ahead and define another equation over here. We'll go ahead and give that W, and then T is going to be equal to W0, like so. Right, and this is going to return, once again, the dew pressure, and that's going to be a YT this time since we're using Y. So this is going to be YT, and then this is just going to be minus the pressure again, because once again, we know that the dew temperature, the dew pressure is going to be equal to the pressure that we have constant, so we're just going to use the root solver to go through and try a bunch of different temperatures until they are both equal to each other, which means that the difference is going to be equal to 0, right? So we're going to, not sure what that's doing, minus P, and then we're going to go ahead and return the root of our EQ, and we'll go ahead and guess 298 again, and then we'll do .x, and then 0 to once again pull it out of the array. Alright, there we go. Make sure that's all running right. Alright, it looks like we're good. And now what we're going to want to go ahead and do is we are going to graph out so that we can see how these dew pressures and dew temperatures and all of that is going to change as our mole fractions over here change. And we're mainly going to be looking at how the benzene changes, since that is going to be our more volatile compound. It's going to have the lower boiling point. So we're gonna see as the percentage of benzene goes from 0 to 100, how does that affect what the temperatures and these pressures are going to be? And we're going to take a look at those relationships. And so yeah, we're going to go ahead and hop into that now. Alright, so the first step that we're going to make when looking at the relationship that the percentage of benzene has on all of these different pressures and temperatures is that we're going to need to create a list for our percentages over here. So we're going to go x1 is going to be equal to np.linspace. This is just going to give us our list of percentages over here. And we can go from 0 to 1 here, right? We can't have less than 0% benzene, and then we can't have more than 100%. So that's going to range from 0 to 1. And we'll get 11 spaces going in between that. And then we know that since there's only 2 compounds in this mixture, we know that the percentage of toluene is just going to be 1 minus whatever the percentage of benzene is. So we know that x2 is going to be equal to 1 minus x1, like so. And then we know that when we are calculating our pressures over here, we are given that the temperature that's going to be remain constant is 393.15 Kelvin. So we'll go ahead and import that there. And then we are going to go ahead and say that our saturation pressure is just going to be equal to the P.Pvap at our selected temperature, which again is going to be 393.15. And this Pvap over here is basically going to be running through our CHE props for the benzene and toluene and giving us the vapor pressure at that specific temperature. Right, and then we're going to need to create a list for our bubble points over here to be calculated at each specific percentage of benzene. All right, and in order to do this, we are going to we know that the bubble point is just going to be equal to the addition of each percentage of the compounds multiplied by the specific vapor pressure of that specific compound. All right, so we know that this is going to be equal to x1 times Psat 0. That needs to be a 0. And then that is going to be added to the same exact thing except for the toluene. So this is going to be x2 times Psat 1. And there we go. That is going to be our list for the bubble pressure. It's simple enough. Make sure that's working. It is. All right. And now we're going to want to go ahead and create our graphs. So we're going to go ahead and create a 1x2 graphing system so that we can put our pressure graphs on the same graph, and then we'll put our temperature plots on the same graph as well. All right. So we're going to go to fig equals make subplots. And then rows is going to be equal to 1, and cols is going to be equal to 2. There we go. And then we're going to add a scatter to this. Just add scatter, and then x is going to be equal to x1. And then our y is going to be equal to our list BP over there. And then we'll go ahead and place this in row 1 and column 1. And we'll give this a name as our bubble point. Let's see if that's working well. There we go. That is going to be our graph for the bubble point. And now what we're going to go ahead and need to do is we're going to need to create our list for the dew point. So we're going to go ahead and create an empty list for now. That's going to be equal to dew point. And now since we're not going to be able to use the x1, since that is representing the mole fractions in the liquid phase, and the dew point takes into account the mole fractions in the vapor phase, we are going to need to do something a little bit different. We're going to be creating a for loop for the y1 and the x1, so we're going to go ahead and write that out. This is again because the dew point takes into account the mole fraction in the vapor phase, so we can't just use x1. But since they are going to have the same number of points, right, it's going to be the same 11 points, we can just go for y1 and x1. And then we're just going to do pretty much the same thing we did right here. We're going to know that y2 is going to be equal to 1 minus y1 because, again, you can't have a mole fraction equal to anything more or less than 1, right? The percentages are going to be equal to 1. And then y is going to be equal to mp.array of y1 and y2. And then we're going to just go ahead and add onto our list using our due pressure equation over here. So we're going to go list dp dot append, and then we're just going to go ahead and go dp of y and t. And that should be running nice for us. Go ahead and shift enter, make sure that's working all right. Alright, gotta get our semicolon in there. Alright, that's looking good. And then we're gonna go ahead and add in our graph over here. Gonna be pretty much the same thing. We're just gonna need to go ahead and change the list BP to list DP. And then we're gonna go ahead and change the name. See how that's looking. Alright, something's a little bit off there. We're going to go ahead and check their equations and make sure we got everything running right. Alright, so I did find our issue that was causing this funky little graph over here. We made a mistake in our due pressure function over here. We had the sum function in the wrong place. We wanted that within the denominator. We did not want that around the whole fraction. So we're going to go ahead and get that squared away. Let's see, make sure all of our parentheses are in the right place. I think that should be working good now. We'll go ahead and check this graph now. And yeah, that's looking more like how we want it. Alright, so now we are going to go ahead and move on to our temperature functions. And for these ones, we'll go ahead and make our lists. These ones are going to be empty lists again as well. There we go. And for this one, we're going to have our pressure being a constant, and the temperature is going to be the factor that's getting changed. So we'll go ahead and import our constant. For this one, it's going to be 150 times 10 to the third, so it's going to be 150 E3. And we're basically going to do pretty much the same steps that we did over here for our due pressure. We are going to set a for loop for Z1 and X1. Because, again, we are going to need to have, it's the same number of spaces, so this is going to work out just fine for us. And then we're going to do Z2 is equal to 1 minus Z2, or Z1 I should say. There we go. And then for this one, we are going to do another append, so list bt dot append. And this is going to be for our bubble temperature function. And then this is going to be using our array functions for our Z1 and Z2. Like so. And that is also going to be using our constant pressure that we have. And it's pretty much going to be the same thing for our due temperature, except we're going to need to replace the BT with DTs. There we go. And yeah, basically what this is doing is this is running through our bubble temperature and our due temperature equations and calculating it based on all of the different possible mole fractions that we're going to have that is this list right here that it's using to go through and run the function. And then it's also using this given pressure that we have, our 150 e to the third, and it's going to go through and it's going to give us our bubble temperature and our dew temperature, and then it's going to add that back to the list, which we are then going to use to graph. So that's basically the logic that's going behind this. And now we're going to go ahead and add our graphs in. So this is going to be the same simple add scatter function, except these ones are going to go into column 2 this time, because this is going to be where we keep our temperature graphs. And then this is going to be the bubble temperature and the dew temperature. And this is going to be list BT and DT. Let's make sure all this is running right. We'll go ahead Shift Enter through everything. Nope, looks like we got a mistake here. X. Let's see, did this supposed to be a lowercase? Probably always get those mixed up. Let's see if this is running right now. Alright, we should be good to go. Hopefully these graphs pop out right. And yeah, that's what we are looking for. And now we'll go ahead and explain and talk through what it is exactly that we're looking at here. Alright, so if we take a look at our temperature graphs over here, we can see that generally speaking, as we increase our percentage of the benzene, which is going to be the more volatile compound, we can see that the temperature needed to be reached to create that first bubble and that first drop of moisture is going to go down. And this is because, once again, benzene has the lower boiling point. So the higher percentage you have, the lower the temperature is going to need it to be to get that first drop of liquid. And likewise, when you have the vapors, you have the system in complete vapors, and you need to find that first drop of water. When you have more benzene, the temperature is going to need to be lower to get that first drop. All right, if we take a look over here at our pressure graphs, we can see that as the percentage of benzene gets higher, then you're going to require more pressure to create that first few drops of liquid and to create those first few molecules of gas. And this is because simply the benzene has a higher pure saturation vapor pressure. All right, so as our percentage of benzene climbs, the addition of these partial vapor pressures over here, this PVAP, that's going to continue to go up, because once again it's a higher percentage, and the benzene has a higher PVAP value when compared to the toluene, so the total value is going to go up. So these graphs make perfect sense, and yeah, I think that's going to do it for today's video. Make sure to smash like and subscribe if you enjoyed, leave a comment, and yeah, have a good one.